So let's discuss perpendicularity tolerances applied to features of size. Okay, so the feature control frame adjacent to the size dimension or attached to a dimension line, that's how we know that our orientation tolerance applies to a feature of size. The diameter symbol is sometimes used for cylindrical features, and the referenced datum features may be surfaces or they may be other features of size. And the RFS established control of the center plane of an axis, whereas the MMC or LMC establish a virtual condition and controls the surfaces of the features. So what does that mean? Okay, so let's talk about perpendicularity tolerances at MMC applied to a pin. Okay, so in this case we have an orthographic view. We have a plate with a pin sticking out of it. The size tolerance is 375 plus or minus 2 thousandths, and then we have a perpendicularity tolerance of 6 thousandths applied at MMC to datum A. Now in this case we're going to need the diameter symbol for this. So what does this mean? It's going to give us a virtual condition first of all. So our virtual condition is the MMC plus the tolerance. So we have 377 plus, that's 377, which is the MMC of this feature, plus the 6 thousandths. That gives us a 383 thousandths tolerance zone. So in which case, here our tolerance zone becomes, we have our datum A, we have our feature axis, and then a tolerance zone becomes this virtual condition. Okay, so if we were to use like a functional gauge to check this part, this feature, what we would do is we would create a simulator for datum A, and then we would create a hole in this gauge part that would be equal to this virtual condition size of this hole. And as long as we put that gauge over top of the pin and touch datum A on the 3 high spots and the pin fit in without binding, and then we know the part works, the part fits, the part does meet this tolerance. Okay, so essentially with a functional gauge like that, we would be checking the inner surfaces, or the outer surfaces of this part, to see if they were in tolerance, and that's what we call the surface method. Whereas if we try to check exactly what the axis is, that's a little bit more difficult. So surface method is the best way to go about checking these things. Okay, so let's expound upon this a little bit more. Verify perpendicular to MMC. So this gets what I was talking about introducing in the other slide was a functional gauge. We can build and use a functional gauge to check this tolerance of the part. And really what the functional gauge is, this is what is shown right here. We have our workpiece, we have some imperfect surfaces, and then we have our pin sticking out of there that's really not quite perfectly parallel, perfectly perpendicular. So we can build this gauge that's built to the virtual condition with a nice datum simulator here for datum A. And really, as long as we were to put that part into this functional gauge, the pin itself was to clear on all surfaces, and we were able to obtain 3-point contact between our simulator and datum A. Bingo, the part is good. So functional gauges can be very easy ways of checking a part that has a tolerance that applies at MMC. Excuse me. Okay, so let's look at perpendicularity tolerance at MMC for a hole. So in the last one we talked about a shaft. Let's talk about the hole now. Okay, in this case we have a drawing would have a datum A here, and then we have a hole. 392 plus 6 thousandths minus 1 with an 8 thousandths true position at MMC. So our first step would be to calculate the virtual condition, which in this case would be our min hole, which is 390 minus the 8 thousandths. So we get 391 minus the 8 thousandths, which gives us 383 thousandths. That's our virtual condition. And then a tolerance zone and the virtual condition are perpendicular to datum A. That's what we're showing right here. There's our virtual condition, perpendicular datum A. We're showing our imperfect part off to the side like this at MMC off to the side, and then it shows our datum axis our tolerance zone axis here. And so how would we check something like this? Again, we can use a functional gauge. A functional gauge would be built, we got this functional gauge here. It's got a plate and it's got a pin on it. The plate simulates datum A, and the pin that sticks out of it would be at the virtual condition of the hole. So as long as we were to take our gauge and put it in to this hole and then see that we have a full 3-point contact with our datum simulator here for datum A, and there was no binding of the pin in the hole, yeah, that would check our part and make sure that it was good at its virtual condition. Let's talk about controlling two cylinders perpendicular to each other. So first of all, no diameter symbol is required on perpendicularity tolerances when applied to a cylindrical feature of size. That's because it controls only orientation. It doesn't really control form. It just controls orientation. So, and it does not control form when the diameter symbol is omitted. So and then we're going to only include the diameter symbol if it's desired to control both the orientation and the form. And so here's an example of controlling two cylinders perpendicular to each other. Okay, in which case we have a cylinder here, and then we have a hole that's drilled through this cylinder. Okay, and we have a perpendicularity tolerance on that. So essentially, I think we would also need a location tolerance for this hole as well, because what we're showing here is the location of the hole is not controlled by the perpendicularity tolerance. And then really what this establishes is two planes, the 7/1000th perpendicularity. It established two parallel planes here through which the center line of the hole must act. So that's how we use this. So we have a perpendicularity tolerance. We have 7/1000ths at MMC, and that really establishes these two parallel planes through which the center axis of the hole must fall. So let's talk about controlling perpendicularity of slots and rails, RFS. This is a little bit tricky too because we're talking RFS. Things are a lot more difficult at RFS. So the orientation applied RFS at a slot establishes control of a center plane. Here's how it would show up on a drawing. We have a datum A here. We have a slot feature of size dimension. We have the perpendicularity tolerance applied to the dimension. So it's applied to a feature of size. And then really, since it controls the center plane of the axis. And so really what we have is 8/1000ths parallel planes perpendicular to datum A. That's where your center line axis has to fall. And then it has to fall somewhere between the 490 mmc and the 510 mmc. So that's what it says. So feature control frame adjacent to the size dimension or attached to the dimension lines, and then the side slots may have form or angular variation as long as rule 1 and the side limits are met. That's shown right here. We can have form variations or angular variations, and then we also know that the center plane must be within the two boundaries established by the two planes. Now, one more slide before I conclude this one. Controlling the perpendicularity of slot and rail sidewalls. Okay, so, when we're talking about this one over here, where we're controlling the center plane of the slot, we aren't talking anything about what the sidewalls look like. So if we wanted to control a surface using perpendicularity on one of the sidewalls, this is how we would do it. We would have this extension line coming off from one of those surfaces, and we would apply the perpendicularity tolerance directly to that extension line. So the perpendicularity tolerance applied to each sidewall directly controls the orientation of each. This example only shows it applied to one, but if you wanted it applied to both, you'd have to show it both because they control independently. And then the tolerance zone of each surface is independent of the other. Okay, so I want to end this presentation right here, and then we'll pick us up with angularity tolerances on slide 42. Thank you.